Check it out now, y'all.
NanoHub U, online instruction.
If you bother to look at the textbook, you'll find that we're almost near the end of the material covered, and there are a few topics remaining. What I like to do is I like to summarize very briefly these remaining topics. I refer to them as advanced topics simply because if you took an introductory course in physics, you probably didn't hear much about any of these topics that we're going to discuss in this lecture, so I call them advanced. And what I like to do is give a brief overview of each of these topics, and then we're going to pick nuclear physics as the point of focus for the remainder of the semester. The reason I picked nuclear physics is because it's a subject that you see every day in the news. You read about it in the newspaper. They use words that have specific meaning, and what we'll try to do is we'll try to put some understanding behind the words that are often encountered when topics related to nuclear physics are presented in newspapers and news stories. So that's the that's sort of the overview of this particular lecture. And what I'd like to start with is a very brief review of the relativistic Schrodinger equation. So if you read the textbook, there's a whole chapter devoted to something called the Dirac equation. And the Dirac equation is nothing more than a relativistic version of Schrodinger's wave equation. And if you want to broadly understand Dirac equation, then I have to remind you the steps we went through to derive the Schrodinger equation, and then I have to show you what Dirac did in order to write his wave equation down for relativistic particles. So to begin the discussion, you'll recall that in free space, classically, the energy of a particle is equal to p squared over 2m, where p is the momentum. To go from a classical picture to a quantum picture, you have to invent operators that represent the various terms in this equation for energy, right? So in particular, the energy operator was defined to be this derivative with respect to time. The momentum operator was defined to be a derivative with respect to space, so it's this gradient operator. And what you can do is you can take these operators, and what Schrodinger did in 1926 is he took these operators and he basically wrote this classical particle description for energy. He wrote that in terms of these quantum operators, and you end up with the non-relativistic Schrodinger equation in free space. Okay? So, how is this modified when you try to take into account relativity and relativistic effects? Well, in a very simple-minded way, you would write an expression between energy and momentum. The trouble is that relationship is not going to be as simple as it was classically. So, if you go back 2 lectures, we've got this very famous equation that says the total energy of a particle squared is equal to p squared c squared plus m squared c to the 4th. So if you tell me the mass of the particle, right, this has to be factored into the total energy of the particle. And this would then imply that there's an expression that you can set equal to 0, which is the difference between the right and the left-hand side of this equation. So you might be tempted to take the same operators that Schrodinger identified and substitute them into an equation of this form to come up with a wave equation to describe relativistic particles. And so that's exactly what happens here. You take the energy squared and you use the energy operator from non-relativistic quantum mechanics, and you get a second derivative with respect to time. You take the momentum squared, and you end up with a factor or a term in the equation, which is a del squared that describes the momentum of the particle. Notice this factor of c shows up. Whenever you see a factor of c, that's an indication that the equation is relativistic. And then lastly, you take this m squared c to the fourth term, right? There's no operator associated with mass, so that just gets stuck on the end of this equation. And so then you end up with a differential equation that looks something like this. This differential equation was proposed by Klein and Gordon in 1926 to describe relativistic particles. And it's now known as a Klein-Gordon equation. It's a very famous equation in physics. The difficulty with this approach is that this differential equation has a second derivative with respect to time in it, whereas Schrodinger's non-relativistic equation has a first derivative with respect to time. So the second derivative with respect to time causes problems, because that implies that you have to know both the wave function at t equal to 0 and the derivative of the wave function at t equal to 0 if you're going to make it a serious attempt at solving this equation. Okay? So what we try to do is from the Schrodinger's discussion of wave mechanics, we said that once you know the wave function psi at t equal to 0, that's all you need to know. Right? And then you can solve for the time evolution of that wave function by reverting back to Schrodinger's equation. If you follow Klein-Gordon's approach, you need two parameters, right? You need two initial conditions in order to solve this differential equation. And so, it's not optimal, right? The point is it's not an optimal formulation of relativistic quantum mechanics. Dirac came along in 1928 and realized that you can take the expression for the energy, the total energy of a particle, and you can write it as a square root of these two terms. This is the c squared p squared term. This is the rest mass energy squared. He realized that you can write this equation in this form, and by introducing two matrices. These matrices are referred to as alpha 0 and alpha sub I, right? And even though this equation is not true algebraically, it's not true for numbers, when you go into this matrix arithmetic realm, you can in fact show that under certain circumstances, this square root of these two terms can be rewritten in this form. Now the advantage of doing that is now when you take this equation and you try to write a wave equation, right, you end up with just a single first derivative of the wave function with respect to time, right? And now we've got something that resembles Schrodinger equation. There's additional terms. Right? There's additional terms. We have to include the rest mass energy of the particle that we're considering. But this is now a first order differential equation. It requires one boundary condition, basically the wave function at t equal to 0. And so this then specifies the relativistic wave equation for a free particle based on Dirac's formulation of quantum mechanics. The virtue of this formulation is that it makes some amazing predictions. In the process of solving this equation for a free particle, the spin of a particle automatically appears in the formulation, and also the existence of antiparticles also appears, right? And so both the spin and the antiparticles were experimentally observed. And it turns out they come from this Dirac equation in a very straightforward way. The other thing I'll mention is that if you take the non-relativistic limit for the hydrogen atom, applying Dirac's formulation, right, you now get a more complicated expression for the energy eigenvalues. So the energy eigenvalues now are non-relativistic energy eigenvalues. You pick up the two terms that you're very familiar with, right? This is the p squared over 2m term. This is the kinetic energy of the electron. you pick up a term which is related to the electrostatic potential energy of the electron interacting with the nucleus. And then you pick up an additional 3 terms that follow out of Dirac's equation. And in particular, the one that's really interesting is the spin-orbit term, which involves the angular momentum coupling with the spin of the electron. All right, so this is something that we had to empirically add when we discussed the non-relativistic wave equation. And it was motivated basically by the spin of an electron. But using the relativistic wave equation, it just comes out naturally. So it's a very nice result. So that's one topic. You'll find a whole chapter devoted to Dirac equation at the end of your textbook. You'll also find a chapter devoted to the fundamental forces in nature. And this is, of course, an extremely interesting topic. If you go back to your introductory course in physics, you probably studied gravitational and electromagnetic forces. But experiments over the years have shown that there must be 2 additional forces. One force is called an electroweak, and then the other force is called the strong force or the nuclear force. And so there can be an extended discussion of these additional forces in nature to end up this course. Let me just say that when you talk about forces when you talk about the electroweak and the strong force, right, you basically have to abandon this traditional field view that's adopted in classical physics. The field view of forces is that there's a source charge. This source charge produces an electric field. The electric field then fills all space, and then if you introduce a test charge, let's say small q2, right, that test charge interacts with this force field to produce a force on the test charge that's just given by the product of q2 times the electric field E at the point where the charge is located. When you start to discuss the forces between, let's say, nucleons, you have to abandon that picture. You have to invent something called a virtual particle. And the concept of a virtual particle is extremely interesting because it allows you to consider a force in terms of a change in momentum with respect to time. And the change in momentum is going to be the change in the momentum that one object feels when a virtual particle is exchanged between it and a second object. So this is very often illustrated as two guys in a rowboat and 2 separate rowboats. The guy in one rowboat throws a bowling ball to the guy in the other rowboat. The net result is there's a change in the momentum with respect to time of this bowling ball, causes the first boat to be repelled from the second boat. When the guy in the second boat catches the ball, he acquires the momentum of the ball, and the boat then also moves in this direction. So the exchange of this bowling ball between these 2 guys causes a net force of repulsion between apparent repulsion, right? Apparently these 2 boats repel one another because this particle has been exchanged. So you can talk about the fundamental forces in nature in terms of the exchange of these things called virtual particles. The point I'll make is that the electromagnetic force, that's the force between charges, right? That's governed by the exchange of a photon between the individual charges. But when you start to get down to the weak force and the strong force, right, you end up exchanging things which are referred to as bosons or mesons between different objects, right? So there's a whole chapter devoted to this discussion of virtual forces in your textbook, and so that's a very brief introduction to what those forces are all about. But if you look at the problem historically, we're sort of getting ahead of ourselves, right? And the path we're going to follow for the remainder of the semester is we're actually going to focus more on the nuclear force and the physics of the nucleus rather than on the physics of elementary particles. And the reason we're going to do that is because historically the nucleus and understanding the nucleus proved to be a tremendous challenge between roughly 1920 and the 1960s and 1970s. So it's a topic that's consumed about 50 years of intense work, and based on those 50 years of intense work, we can present some nice summary results. Right? What we're attempting, of course, to do is we're attempting to understand the nuclear structure of an atom much in the same way that we understood the electronic structure of atoms. And of course, for the electronic structure of atoms, right, we've got Mendeleev who organized the periodic table and gave us a way to think about the chemical activity of atoms that we find, of elements, of chemical elements that we find in nature. The question is, how do we learn about the internal nuclear structure of an atom? And then by this I mean the nucleus, right? How do we learn more about the properties of a nucleus that comprise each element in this periodic table? And the answer is we have to do scattering experiments. This was the insight that came about in roughly 1910, 1911. The idea is really, really simple, right? If you have a box, right, and you want to know what's inside that box, one way you can sort out that question is by firing projectiles at the box and measuring the results of the trajectories of the projectiles after they interact with the box. If you find that most of the projectiles pass through the box with a trajectory unimpeded, you are then led to believe that the box might contain some soft, fluffy material. Right? If, on the other hand, you find that a significant fraction of these projectiles actually bounce off at odd angles, some of them actually bounce back in the same direction from which they came, then you might conclude that the box is filled with a very hard, rigid material, that there's certain regions of the box that deflect these incident particles in a rebound, right? They actually cause these particles to rebound from the target. So that's the basic idea. This idea was of course carried out in 1911 by Rutherford. What Rutherford did was he took at that time it was radioactive material. They didn't completely understand radioactivity in 1911, but they knew that there were energetic particles that were emitted from some elements. So he took the element radium, produced a collimated beam of energetic particles. He allowed that energetic beam of particles to interact with a gold foil, and he measured with a counter the particle scattering as a function of the angle theta. And surprisingly, what he found was that occasionally some of these energetic particles emitted from the radium were backscattered by the gold foil. A large majority of them just passed straight through, but occasionally he measured this backscattering through very large angles. And he concluded, right? He concluded on the basis of this that there were heavy objects in the gold foil, and these heavy objects were about 10,000 times smaller than the dimensions of an atom, right? And these heavy objects presumably contained the nucleus of the gold atoms. So that was the fundamental conclusion that came from Rutherford's experiments. That was 1911. By 1935, we started to have a reasonably coherent picture of what an atom consists of. The basic idea is that electrons orbit a nucleus. The nucleus is comprised of protons and neutrons. The nucleus is the very heavy object that caused these energetic particles from the radium source to be backscattered. So these nucleons were very massive, and they had to contain positively charged protons to balance out the electronic charge that existed in these quantum orbits that cause the electrons to revolve around the nucleus. By 1935, the fundamental properties of the electron, the proton, and the neutron were reasonably well understood, and the interesting questions started to arise about how these protons, which were positively charged, how they could be packed into such a small distance and not be repelled one from another by the electrostatic forces that surely must exist between the positively charged protons. In addition, when a neutron was discovered in 1931, the question became what was the role of the neutron in forming this nucleus? I mean, why is there a particle in nature that has zero charge, has basically the same mass and same charge as the proton? How does that factor into the nucleus? So it's kind of interesting historically to look at how these various elementary particles were discovered, and I found this very nice chart on the web. It shows that the electron was the first elementary particle to be discovered. That was back in the 1880s. It took until about 1919 before the proton was discovered. It took another 10 years for the neutron to show up. That occurred in 1931. But then after that, everyone started to look carefully at these various scattering experiments. The presence of different particles were observed, right? And that culminated in the 1950s and 1960s by these very energetic particle colliders that produced just a plethora, just a huge number of these particles. And of course, this is the domain of high energy physics, right? And understanding how to organize these different particles that were discovered. That's what high energy physics is all about. What we're going to do is we're going to take a much simpler approach, right? We're not going to worry about all the details here. We're going to focus more on the mass of these elementary particles, and we're going to consider how particles are organized by mass. And the answer to that question is there are two fundamental types of particles, which are referred to as leptons, right, and hadrons, right? The leptons are the less massive particles. They're subject to what's referred to as the electroweak force, and they do not feel the strong nuclear force that binds this nucleus together. So an example of a lepton is an electron, right? Electron is a fermion. It's an elementary particle, and it does not feel the strong nuclear force that holds the nucleus together. The hadrons, on the other hand, are much more massive particles. They're subject to these strong nuclear forces, and these nuclear forces are carried back and forth between the hadrons by these mesons, which explain a lot of these elementary particles down here. These are the force carriers that actually bind protons to protons and protons to neutrons. So this is the general organization of these elementary particles by mass, right? It's a very, very high level view. And what we're going to do in the next few weeks is we're going to focus on trying to describe to you some of the fundamental properties of the nucleus of an atom. We're going to describe nuclear matter. We're going to talk about its density, mass density, and charge density. We're going to try to give you some understanding about the isotopes and binding energies of these different nuclei. We'll talk a little bit more about nuclear forces in the nuclear shell model, because it turns out these nucleons are organized in nuclear shells. We'll talk a little bit about radioactivity and how these nuclei disintegrate. And then we'll end up with this topic where we'll actually discuss fission and fusion reactions, try to give you some insight into why these nuclei are unstable, and when they split apart or when they're joined together, they generate a tremendous and unbelievable amount of energy. So that'll be a few lectures on nuclear energy. So that'll take us to the end of the semester, and it'll give us a focus for what we're going to discuss. And when you come back and listen to the next lecture, what we're going to do is we're going to start to describe the nuclear characteristics of nucleons that comprise the chemical elements in the periodic table. So thank you for listening to this lecture, and come on back, because we'll start a brief discussion of nuclear physics in the next few weeks.